All right, welcome back to the third part of our four-part video series. And in this one, what we're going to be doing is we're wanting to assess, basically what we're doing is we're going to plot a Bode diagram. We're going to walk through what a Bode diagram is. We've already started to explain the concepts of it in the previous video at the end of it. And really, you being able to use it to assess the stability or instability of our system, and at which frequency it would become unstable. If so, where would hit a crossover frequency, at what frequency that would happen at, how much phase margin we have for wiggle room. Things like that is what we're going to dive into in this video. Before we do that, I do need to make a point of clarification. From the last video, I said the tangent for the phase lag, it is not the tangent, it is the arctangent. So that is just a point of clarity that I want to make regarding how to assess what the phase lag is. It's the arctangent, not the tangent. So that's just a quick point of clarification before we now dive in to all the good stuff before us here. So let's go ahead and plot this out first, and then we're going to walk through each of the particular things as we'll explain as we go here. And so first we're going to bring in our frequency, and so instead of it just being one particular thing, we're going to analyze it, and we analyze it in log space just due to clarity on the graphs. Let's say 100, and then next up, what we're going to do here is actually bring in our Bode tool, our Bode diagram. So first is we're going to be assessing our frequency. We're going to be assessing our amplitude ratio in decibels. We talked about how to get that amplitude ratio, which again was linking the Laplace transform with the Fourier transform, and basically the Laplace transform, that S, getting converted into a JW, because what the Fourier transform is doing is it's a couple things in addition to the Laplace transform transfer function. What the Fourier transform is doing is it's able to assess from negative infinity to infinity as the range, but it's also able to assess in both the real and the imaginary realm, which allows us to then successfully assess our sine and cosine waves when we decompose signals down into the sum of the cosines and the sines. And so that's why that matters. And so the amplitude ratio is the way we find that amplitude ratio. Again, is if we go back here, this is the amplitude ratio, the absolute value of whatever our transfer function was from our Laplace transform converted into our Fourier transform, equaling the square root of the real component squared plus the imaginary component squared. That is our amplitude ratio. And in this case, we'll assess both in decibels and in the amplitude ratio. Ultimately, we're going to leave it in decibels. Okay, so the next, we've got W, we've got dB, we've got our phase. And here's where we're going to bring them in. And what we're assessing here is we're going to go ahead and do it as an open loop response, meaning we're not going to close it all the way to the error part. We're going to rather be doing an open loop where we're assessing our GC, if it doesn't lag for me here. Oh, it's really lagging here. Come on. The internet is nice and slow at the top of the house here. Anyways, it doesn't look like it's catching over, but the point is on our diagram, we've got our set point, then our error, then our GC, then our GP, and then getting kicked back through our GM, our measurement device. The open loop that we're assessing here is our GC. Oh, here we go, finally. Our GC and our GP, and then our GM. We're not going to close it all the way with the error part. And so let's go back to our code here. So we're assessing the forward at the frequency. All right, great. So now let's go ahead and get, if we want to convert, if we want to assess the amplitude ratio, to convert it from amplitude ratio to decibels and back would be right here. So amplitude ratio is assessing, well, the amplitude ratio, and decibel is assessing the power ratios. And so that's the relationship between the two there. Now, as far as graphing this out, we can pull a few things here that we've already done. All right, so we can change a few things up here. Okay, so here we're bringing in our tools for plotting. We're going to bring in 2 rows and 1 column. The reason for this is because in the top row we're going to assess our dB, so our amplitude ratio in decibels. In the second row we're going to be assessing our phase lag, and then what degrees the phase lag is occurring at. And then for both the x-axes, it's going to be the frequency. And so we're assessing both at any one particular frequency. And so then what we're saying is that when any one particular frequency, what is both the amplitude ratio at that point and the degrees of the phase lag. So let's go ahead and code that out here. So we've got, this is going to get changed to our frequency. Our top graph is going to be our dB. The name is going to be dB. We're going to stick this in row 1, column 1, and then, oh, come on, there we go. In our second, we're going to have also along the frequency line, the Y, what we're assessing here is our phase lag, and then this is going to be in row 2, column 1, and this is going to be called our phase. Now we're assessing this on, oops, dang it, no. We're assessing this on the logarithmic scale, so let's go ahead and update that. Oops. Update x-axis, and the type is going to equal our logarithm. I didn't get to have the grand reveal anymore because I didn't have accidentally pressed enter. We're going to shift our layout to a higher height. All right, and let's shorten that width to 400. There we go. Okay, so what we see here is, well, this is our Bode diagram. And so what this means is, what we can evaluate now is, here is our phase. And so we can look at and say, does the system ever cross negative 180 degrees? Because if it doesn't, if it's always above that negative 180 degrees, then we never end up getting that crossover frequency at which the system becomes unstable. So if we're always above negative 180 degrees, then great. If the curve were to bottom out at negative 160 or whatever, anything above that, anything above negative 180, our system is going to have stability. It's going to eventually stabilize out. But if we look at this, and if our phase does ever dip below negative 180, then the frequency at which that happens, the frequency at which we've crossed negative 180 degrees, that frequency is called the crossover frequency. We've gone to the point of no return, potentially. We don't know. We'll find out. So here we do see that we dip below negative 180. So here we've got, at that, it's roughly 1.15. So then what we do is we then assess up here in our amplitude ratio, and we say at 1.15 we're wanting to look, and we're wanting to ask, is our ratio greater than 1 or less than 1? If it's greater than 1, we've got a problem. We've got Houston, we've got a problem, because what happens is the output is going to continue to grow, and that signal is, so the input's going to go through the process is going to increase the signal, it's going to get fed back into our loop again, and then that's going to continue to increase, right? Then the input signal is now increased from whatever the output did, and then that becomes the new input. Then that input gets increased again from the process, and it just continues to increase on and on and on into infinity, and so our system is completely unstable then. And so that's what occurs if our magnitude is greater than 1 at the crossover frequency. Here in this case, we're looking at 1.15. we have a amplitude ratio that's less than 1, which is great. So that should suggest to us that our system is going to eventually stabilize out. That might not be right off the bat, but eventually any deviation from standards from the steady state, it should eventually, after a few oscillations or however many oscillations, it should eventually stabilize out because the output continues to be smaller than the input signal, and it decreases until it hits that finalized state from the controller. And so looking here, we should have a stabilized system. So at the crossover frequency, it does cross negative 180 degrees, but at the crossover frequency, our amplitude ratio is less than 1 here. And what we can then say is, if we assess this in contrast with what we've already previously looked at, let's go ahead and see if this is the case. Does it stabilize out? And indeed we see this is the case. We do have oscillations, but they get smaller and smaller and smaller, meaning our output continues to get smaller than what it's receiving as the input. It's continuing to decrease it. And we see that the oscillations continue to get smaller, and we eventually are reaching a stabilized state. Doesn't happen right off the bat, but we do see that we're reaching stability eventually. So this confirms what we just confirmed in our Bode diagram. We look at our Bode diagram, we say it should be stable after a certain point. We look up here and we see that that is indeed the case. Now, how much range do we have? How much wiggle room do we have? And wiggle room is referred to as our phase margin. So we'd say, okay, well, when we look at our amplitude ratio, when it's 0, well, it's hard to get exactly 0 on here without zooming in, but let's just say, so when our amplitude ratio, this is fine, I guess close enough. So at 0.79, let's go ahead and go down here at 0.79 on our frequency. Okay, so when we are at 0.79, our frequency was, our degrees is negative 173. Now, so we can probably bump it up a little bit because we weren't exactly at 0. But what we're saying here is when our amplitude ratio is at 0, the moment it would become negative and or the moment it would become positive, and we've got a problem with our output increasing the input signal, that's kind of the point of which we need to assess when would it go from stable to unstable. And here in our particular system, we see that we have about 10 degrees, 7 to 10 degrees of wiggle room, meaning we've got about 10 degrees left before we've hit our crossover margin, before our system has become unstable, and or before we've hit that crossover frequency, before which we need to be concerned with stability versus instability. So let's go ahead and see here. So we're going to recalculate now our Bode diagram for our open loop response that we have here with a controller gain of Kc equals 3. And let's go ahead and see what happens here, and then confirm with what we've previously graphed out to see if that does indeed match what we'd expect. Okay, so we're gonna shift our Kc. It's currently at 1. We're gonna shift it over to 3. So real quick, before we shift it to 3, let's again just assess the numbers here. So our crossover frequency is 1.15. At 1.15, our system is currently negative. So our amplitude ratio in decibels is below 1, meaning it should stabilize out, which is what we saw to be the case here. Now, if we shift our Kc to 3, for example, and we rerun the numbers and check our Bode diagram, what we see, there we go. Okay, what we see here is we still have our crossover frequency at 1.15, whereas before it was like negative 6.5 something. Now, at 1.15, we're at a magnitude, a decibel amplitude ratio of 2.98. And so we're greater than that 1, that amplitude ratio of 1, meaning that our output is going to continue to be larger. It's going to continue to increase the input signals that it receives. The process is going to continue to increase that input signal, so the output signal is going to be greater than the input. And so what we should see in our system is we should see oscillations that continue to increase on into infinity, because we've been shown from our Bode diagram that at the crossover frequency, our amplitude ratio is greater than 1. So let's see if that is the case, which it is. I ran it all already. Whereas before, we saw that it kind of worked its way down to 1 and eventually bottomed out and stabilized out. In this case, what we see is the output signal continues to increase. So it keeps amplifying up that input signal at greater and greater amounts. And this just continues to increase on and forever. So we're going to have an unstable system. And oops, wrong one. There we go. So yeah, so that covers the things we were trying to hit. So let's go ahead and bring it back down to 1 here and just confirm that at 1 our system stabilizes out. What that shows us on the reverse end is that our Bode diagram is going to be less than a magnitude of 1, less than 1 for the amplitude ratio at whatever the crossover frequency is. And that is what we see here. At the 1.14, it's less than 1, meaning our system is going to stabilize out, which is what we see to be the case. So that is our walk through the Bode diagram, which is just this incredible tool for just frequency response analysis, to be able to say, we've got an input coming into our system. What is the amplitude ratio going to be? What is the phase lag going to be once it runs through a process and the output? Then we're able to say, does it hit a crossover frequency? If so, does it ever hit negative 180 degrees at any point? If so, what is frequency? At that frequency, is our amplitude ratio greater than 1 or less than 1? If it's greater than 1, it's going to be unstable because the output is continuing to increase, which we saw. If it's less than 1, we're going to have a stable system because the output is going to continue to be smaller than the input, and it's going to be able to stabilize at any deviations from our steady state back to a new steady state in our system.